afternoon, good evening, wherever you may be in this world. My name is Martin Ottinger. I'm the Principal Manager for Carbon Capture within the Global CCS Institute, and I'm a member of the Institute's project team liaising with CCS projects around the world. I'd like to welcome you all, our international audience. We do have attendees from around the globe. For your information, this webinar is being recorded and will be made available on our website in the near future. We welcome questions asked through the presentation. These will be moderated. The topic we'll be discussing today covers the fundamentals of chemical looping carbon capture and the state of play regarding this promising type of capture technology. Today, Carl Bozzuto will share his perspective on the technology readiness of chemical looping carbon capture as the world edges closer to commercialization. I'd just like to give you a little bit of background in regard to Carl. Carl, who works with the Institute on Carbon Capture related matters, is from the East Coast of the United States. Carl, the retired Vice President of Technology within the Power Environment section at Alstom, has over 40 years experience in technology development and engineering, having worked in the utility industry in North America since the late 1960s. Carl also worked at ABB Combustion Engineering Inc. for many years. Carl holds both a Bachelor and Masters of Science in Chemical Engineering from the Massachusetts Institute of Technology and remains involved in a number of MIT research programs. Carl also has a Masters of Management Science from the Hartford Graduate Center. Carl remains very active in a number of professional associations, including the Council of Industrial Boiler Owners, the Combustion Institute, the American Institute of Chemical Engineers, and the American Society of Mechanical Engineers, ASME. This webinar will be of interest to a general audience who seek a solid introduction to a promising low-energy penalty chemical-based carbon capture technology, but also to utility owners keen to understand the current state of play. In regards to questions from the audience, we will endeavour to get through as many questions as possible in this session. All attendees are welcome to submit questions through the discussion by submitting them through the GoToWebinar control panel on your screen. Please be aware that we may not be able to answer all your questions today. We will aim to answer all relevant questions which add to the discussion in the very near future. As I said previously, the webinar will be recorded and available on our website along with the slides used in the next few days, and the Institute will email you when it is available for download. Without further ado, I'd like to now hand over to Carl Bozzuto.
Okay, welcome everyone. We're going to spend the next half hour or so talking about chemical looping combustion, starting out with how does the technology work, and in particular, chemical looping combustion, our goal is to separate the combustion process into two steps. In one, we'll react a fuel with an oxygen carrier to make CO2 directly, and then in the other reactor we'll oxidize the oxygen carrier back up, put oxygen back on the chemical involved, and loop that back into the first reactor so we can run the process again. So on our first slide, we see the two reactors, an air and a fuel reactor, and in the air reactor we bring in air, and we're going to react that with an oxygen carrier. Candidate carriers are metal oxides and calcium sulfate sulfide, and our goal there is to put oxygen onto the oxygen carrier and then send it to the fuel reactor. And let's see, how are we going to advance the slide? All right, we're not advancing. Here we go. All right, so in the air reactor, you see the oxygen reacting with the carrier, and the depleted air is exhausting from the top of the reactor. The typical reactor temperature would be around 1,000 degrees C. And we're going to take that carrier and bring it to the fuel reactor. You can see in the fuel reactor, we're going to bring in the fuel. The fuel will react with the oxygen, and we'll make CO2 directly. And that temperature is going to be running about 100 degrees centigrade lower than the air reactor. Since we make CO2 separately, we now have CO2 essentially ready for sequestration. There's a minimal amount of preparation. We have to get the water out, and it has to be compressed. But otherwise, ready for sequestration. Ash is discharged, and then the solid material that's carrying the oxygen brings the carrier back to the air reactor, and we replace the oxygen that was used. So the little blue dots are the oxygen, the orange dots are the carrier, and the material goes around basically in a loop. In Europe, the primary oxygen carrier is metal oxide based. In the United States, Alstom Power is working on a calcium sulfide based carrier. Should point out that calcium sulfate would be the oxidized product, and calcium sulfide would be the reduced product. And calcium sulfate is nearly 50% oxygen, so it's a somewhat better oxygen carrier than air. This whole process then can work without the benefit of an air separation unit, and it also has the benefit of operating at a temperature that is typically higher than the steam temperature, and so any inefficiencies in the looping process would be rejected to the steam process. And so the goal of this operation is to carry out these reactions with a minimal energy penalty. In fact, we should be able to get down pretty close to just the penalty for compressing the CO2. Okay, let's see if we can get the next one. So, where are we in the demonstration or development process? There's been testing done at a very small scale, a 2-inch reactor for chemical looping. But the traditional equipment, fuel and limestone preparation, circulating fluid bed steam generators, conventional gas cleanup, and power block are all relatively existing technologies. Our goal would be to basically substitute the traditional PC or circulating fluid bed steam generator and gas cleanup with the chemical looping, and then have a CO2 recovery option. There's quite a bit of flexibility with the chemical looping process. Initially, we're looking at chemical looping combustion. In this case, we use an excess of the calcium sulfate that's going to the reducing reactor where we react it with the fuel, and the product gas is CO2. Hot solids are circulated to control the temperatures. But we have options for gasification and hydrogen production as well, depending on how much calcium sulfate is circulated between the air reactor and the fuel reactor. In the case of making hydrogen, we can also use limestone in a calciner and make that a third loop of calcium carbonate and calcium oxide for CO2 and hydrogen production. Again, you can see in option 1, calcium sulfate goes to the reducing reactor or the fuel reactor. Coal and limestone are fed to that reactor, and CO2 is produced. The hot solids of calcium sulfide are circulated back to the oxidizing reactor, where we bring in air, generate the steam, and essentially nitrogen is the gaseous product. In the case of making synthesis gas, we would reduce the amount of calcium sulfate going to the reducing reactor and add some steam, and that would give us synthesis gas. And in the case of hydrogen, we would add a calciner, making the CO2 off the calciner, and use the calcium sulfate and steam to produce hydrogen from the reducing reactor. The relative economics and the reason why we have such an interest in the technology, if we look at a CO2 allowance price or a cost of CO2 and compare that to a calculated cost of electricity, we can see if we just look at the dotted blue lines that we're talking about, a relatively low cost to produce the CO2 and competitively generate electricity. In this case, the figures would indicate less than $15 per ton of CO2 would make this technology attractive. This reference is from a DOE study that was done initially starting in 2003, and the figures have been corrected, in this case up to $2006. In particular, one of the reasons for cost savings is that the volume of the reactors and the weight of materials is significantly less. In comparing the building volume, roughly half the volume, and in looking at the weight of materials, approximately 2/3 of the weight. This allows for material savings in addition to the energy savings that are achieved with the chemical looping process. It's also possible to do retrofits with the technology. Again, if a synthesis gas or a hydrogen fuel is produced, that fuel could go directly to an existing boiler, or there could be some integration, as in the second case, with the steam system of an existing plant and bypassing the existing boiler. So this, in principle, the technology is not limited to brand new plants. In the U.S., Alstom has done considerable amount of testing on a 65 kilowatt thermal system at about 2 inches in diameter. The equipment was built and paid for by Alstom, and some of the test work was supported by the United States Department of Energy. Basically, this was a full looping system, but due to the small size, the reactors were electrically heated. So the so-called autothermal operation of the plant was not demonstrated, but the chemical reactions and the ability to loop the solids between the two reactors was successfully completed. In support of that test facility, both a 15-foot and a 40-foot cold flow model system was set up. The real development activity for chemical looping is in controlling and moving the solids around between all these reactors and being able to successfully start them up and control the solids appropriately throughout the entire load range. And so flow modeling of the solids and the solids handling systems is fairly important to a successful operation of the system. The U.S. DOE test program came in 3 phases, including the cold flow model testing. And as a result of the successful operation, Alstom constructed a 3 megawatts thermal plant, and that plant is currently being tested in the Alstom test facilities in Windsor, Connecticut, in the United States. In Europe, a 1 megawatt thermal test facility is about to be tested, and that technology is focused on metal oxides. The approach there is to use conventional circulating fluid bed boiler reactors and use a metal oxide, maybe something like ilmenite, which is a iron and titanium oxide, as the oxygen carrier, and circulate the solids appropriately. The current reactor in Windsor, Connecticut operates at about 1,000 pounds or a half a ton an hour of coal. It's designed to be able to operate in any of the 3 modes: combustion, synthesis gas, or hydrogen. The unit has been built. A number of tests have been run. We've had 2 series of modifications to improve the control of solids and the feed of the material to the reactors. The most recent testing has been aimed at verifying the chemical rates in the reducer, which was done successfully. Additional testing will be needed to demonstrate the autothermal operation, which means the temperatures in both reactors reach steady state on their own, and that we can generate a relatively pure CO2 with very little CO and most of the carbon staying in the reducing reactor, and then in the oxidizing reactor minimize any release of SO2 from the carrier. Should those again be successful, that would minimize any treatment of CO2 that would be required, and the depleted airstream would require essentially no air pollution control system other than particulate. Again, another means of reducing the overall cost of the plant. At 3 megawatts thermal, we're still at a pretty small size. You see the inside the red circle the size of a person, so it's pretty good size equipment, but it's nowhere near a commercial size, so we will need an intermediate step, perhaps in the 30 to 50 megawatt range to demonstrate the technology before getting into the few hundred megawatt size range and commercial operation. Again, it's important to take this development in steps. Handling of the solids and controlling the reactions is still in the learning stages. We've had a couple of hiccups, if you will, in handling the solids at the plant, and so we've already been through a couple of stages of modifications. This is a simplified mass balance to give you some idea of the coal and limestone flows, the amount of air, so roughly 4 tons an hour of air, but the recirculating flow, you can see at 170,000 pounds an hour is a considerable amount of solids moving back and forth between these loops. And making sure that the coal, the calcium sulfate, the limestone, etc., all goes where you want it. That's the key to making these reactors successful. So you can see in this diagram in the blue on the left, basically the fuel reactor or the reducer, and CO2 being produced at the top exiting on the left. And in the orange, the air reactor or the oxidizer, and depleted air or essentially nitrogen being released to the right. And then each of these reactors has to transfer solids from one to the other. A little larger look at the prototype, the 3 megawatt system, and you can see the location of the primary and secondary cyclones, the various dip legs to get the solids back into the reactor, the seal pots, the fluidizing section underneath, and the crossover lines to bring the solids from one reactor to the other. In this particular case, an existing fluid bed reactor was used and modified to make the entire system, again, to save a little bit of capital cost. In the European system, there have been a number of programs starting with 10 kilowatts thermal testing and leading up to the 1 megawatt system that's been built at the university in Darmstadt in Germany. This program has the nickname Eclair, and it's not the dessert. In French, Eclair means to clarify, and it stands for emission-free chemical looping coal combustion process. There are a number of participants, including Air Liquide, Vattenfall, Syntef, and CSIC. That plant construction is relatively complete, and they're in the startup process. They plan to be testing for a period of about 4 years. In this case, metal oxide is the oxygen carrier, and so in the air reactor, the metal is oxidized to its fullest extent. The hot metal oxide would then travel to the fuel reactor or reducing reactor, where it would be reacted with fuel. The carbon will take the oxygen from the oxygen carrier, leaving a reduced metal oxide, and form the CO2. And the now reduced and relatively cool carrier would be returned back to the air plant to be reoxidized. The equipment, you can see the groundbreaking. So it was built in a brand new facility at the university, and all of the pieces were built off-site and shipped to the university for installation. Again, there is a supporting cold flow model of the chemical looping system at the University of Compiègne in France, and this cold flow model is a complete replica of the 1 megawatt thermal loop. That just gives you a general arrangement of the 1 megawatt pilot plant. You can see there's a multi-level construction. So we're getting close to the end of time. Chemical looping combustion is a potential breakthrough technology by operating the reactors at a temperature that's higher than the steam temperature. Essentially, any of the inefficiencies in the separation and capture of the CO2 show up as heat rejected to the steam cycle, where at least some of that energy can be recovered. the calculated figures show an energy penalty of less than 10% for a chemical looping plant. The program is global, and so there's both metal oxide and limestone or calcium-based carriers, and prototypes at the 1 to 3 megawatt level have been built and are being tested in the U.S. and in Europe. There is also a fair amount of interest in a number of countries. Scandinavia has the smaller 10 kilowatt and 100 kilowatt systems. China is testing a 100 kilowatt system. And there are universities in the U.S. that are looking at bench scale programs. And currently the United States Department of Energy is looking for the possibility of an industrial-based program, perhaps to get one of those early demonstration units at the 25 to 30 megawatt level. With that, I believe we can turn control back over to Martin, and we can start attempting to answer some of your questions. Let's see if I can get that one.
Thank you very much, Carl, for what was a very, very interesting presentation, and certainly we've had a number of questions that have come through in regard to chemical looping, combustion, and oxygen or CO2 removal. Carl, we have a question from Diana Kennedy from the University of Newcastle, and her question is, how are high temperatures of combustion created in the unit and then maintained?
Okay, the air reactor is where the heat liberation occurs. And so when oxygen reacts with the oxygen carrier, it generates heat. The amount of solids recirculation in the entire system essentially determines the level of the temperature that can be achieved. So we're shooting for 1,000 degrees centigrade in the air reactor, and we recirculate a substantial amount of solids over to the fuel reactor. That, of necessity, consumes some heat, so the temperature drops about 100 degrees centigrade, and then the solids are brought back. In that simplified flow diagram, we were recirculating about 170,000 pounds of solids, where we're only reacting 1,000 pounds of coal and 8,000 pounds of air. So it's the recirculation of solids that controls the actual temperatures that are achieved.
Okay, thank you very much, Carl. Carl, if you don't mind, I've got a question for you as well.
Sure.
What do you see as the key benefit in terms of equipment of a chemical looping combustion facility versus a conventional oxy-combustion plant?
The chemical looping plant allows for essentially the use of oxygen without the need for an air separation plant and the associated energy penalty and equipment cost. And so essentially we're doing the reactions in what one might consider conventional fluid bed equipment, and not adding either a full scrubbing system or an air separation plant to the total cost of the plant. The goal then is to have a power plant that costs not very much more than a conventional plant and have only a minor energy penalty, less than 10% if we can do it successfully. And so enable carbon capture for a relatively low cost. Our initial estimates were somewhere between $10 and $15 a ton of CO2.
Okay. Okay, that's very good. And Carl, if you don't mind, I've got one other question from within the institute. What is the thermal efficiency that will be expected from a chemical looping combustion power plant, assuming that you had CO2 compressed and available for carbon transport and storage?
Right. Okay. The preliminary estimates, if we started with a conventional present-day supercritical pulverized coal plant, and we had a thermal efficiency of about 40%, or in other words, a heat rate of around, 8,400 BTUs per kilowatt hour, if you will. We would expect the chemical looping systems using the same steam conditions to have a thermal efficiency of about 36%, or a 9,500 BTUs per kilowatt hour heat rate.
Right. That seems to be a significant improvement on other expected efficiencies of conventional coal-fired power plants fitted with carbon capture technologies.
Right. Our early studies, the energy penalty was in the neighborhood of, let's say, 25 to 30%. So we were seeing capture plants with overall efficiencies down at 25 to 28%. There have been improvements to those technologies, so today I would say we're probably in the range of a 20% energy penalty. So again, if we started out with a 40% efficient supercritical plant, we would end up with a 32% efficient carbon capture plant using either amine technology or oxygen firing. And so with the potential for chemical looping to come in the range of 36%, or perhaps even a little bit better, there was enough potential gain to warrant a major research and development effort.
That's very interesting, and I think that's a very interesting point in regard to that, what is a significantly improved thermal efficiency of the facility. I've got one last question, Carl, and that's again from within the Institute. What about the water usage expected from a CLC power plant compared to, say, a conventional coal-fired pulverized coal boiler type power plant?
Presuming again that the reactions are successful in minimizing any SO2 release from the oxidizer reactor, that means that essentially the nitrogen that's escaping from that doesn't need an SO2 scrubber, and so the makeup water to the SO2 plant would be eliminated. On the other hand, the slightly reduced efficiency because of the compression, that would require some additional cooling water, so the cooling tower load would go up. Net, I would say it's a 5% increase.
Okay. Okay, thank you. We have another question here from Alan Chambers, who asks, what is the status of development for applying chemical looping combustion with gaseous fuel, such as methane or refinery gas?
project in Europe with the metal oxides. One of the test programs or test campaigns expects to use natural gas or refinery gas and not Norsk Hydro, but the Norwegian oil company have expressed interest. There's been some testing at the University of Chalmers on gas, but I would say at the moment we're again looking at the 1 megawatt thermal facility to give us the primary information. So that's about the stage that we're at now. It would still need to be a 25 or 30 megawatt level, whether you treat it as megawatts or just as the amount of fuel being tested step that would be required before commercialization.
Okay, thank you. We've got one question from George Boris from EPRI. What are the attrition rates for the calcium-based and metal oxide?
In the metal oxide, we haven't run long enough to get a final estimate, but in our calculations we're using basically one turnover of the metal oxide for every 6 months. In the case of the calcium oxide, from everything we can tell, at least for most limestones, when we add limestone to the reducing reactor, we capture the sulfur. And so that limestone has to be removed from the system. And so we're always making up fresh limestone. And so to date, the attrition hasn't been an issue. Now there's found to be some limestones that will experience a much greater attrition rate, and the answer is there is just not to use that particular limestone. We experience that in present-day circulating fluid bed technology as well. So it's again, it's dependent on the limestone, but in terms of the reactivity of the calcium, we haven't seen a degradation in the looping experiments we've done thus far.
Okay, thank you for that. I guess we'll have probably have to make this one the last one. We have a question from Chiranjib Saha, who has asked, are there any measurements to indicate the conversion of the oxygen carrier between reactors, or conversion difference of the oxygen carrier between reactors?
I presume this is talking about the rate at which oxygen will be released from the oxygen carrier, whether it's a metal oxide or a calcium-based system.
Yes, that might be
Most of the data that we've seen thus far indicates that the release of oxygen is generally much faster than the conversion of the carbon, because in the reducing reactor, essentially a gasification step has to occur in order for everything to get going, and so that seems to be the rate limiting step, and the release of the oxygen from the carrier is relatively fast. Roughly about a dozen different carriers have been tested, and we haven't seen one that was slower than the gasification rate.
Okay, okay. Do we have time for one more question? I guess this is one final question from George Boris, is how do you separate the coal ash from the oxygen carrier?
In the case of the limestone, we have to withdraw a certain amount of limestone for the sulfur we capture anyway, and we take some ash along with that. In the case of the metal oxide system, we're primarily looking at density difference. So the metal oxide that currently being used, the ilmenite, is about 3 to 4 times denser than the ash. And there's a fluid bed, bubbling fluid bed that's being used for segregation.
Okay, thank you, Carl. And look, I'm sorry we're going to have to leave it there. We're sorry we couldn't get through all the questions, but just to our international webinar audience, we will continue the conversation with Carl and circulate his responses. So if you have any further questions, please submit them to Angus Henderson and send via the Institute's webinar inbox. Please feel free to send it to that email address. That's webinar@globalccsinstitute.com. I'd just like to thank you all. Thank you, Carl, for your excellent presentation. Thank everyone who's been a webinar participant for your attendance. And again, a reminder that the webinar has been recorded and will be available on our website in the next few days, along with the slides used. A copy of the presentation will be available for download from our website under the Publications tab. I certainly hope that you found this webinar valuable, and once again, thank you to Carl for presenting. I'd like to wish everyone goodbye wherever you may be in the world. Thank you.
Thank you.